Hello everyone, welcome to part 3 of the Hidden Markov model video series. So in this video we are going to talk about the decoding problem, which is the problem number 2 of the HMM, and we are going to use Viterbi algorithm to solve this problem. So let's dive in. So first of all, we are going to go through the same example and we are going to use this to actually illustrate the entire algorithm and the process of decoding. So we have the early, mid, and late stage cancer as the hidden states Q1, Q2, Q3. We have the low, moderate, and high ctDNA level as the observations, which is V1, V2, and V3. Then we have the transition matrix, which denotes the probability for transitioning from one state to another. And we also have the emission matrix, which denotes the probability of observing a certain ctDNA level, given that we are in a certain state. And finally, we have the initial probabilities. So this is the HMM. So N, M, A, V, pi, and this is the HMM model parameters that denote the probabilities. So we also saw this example before, where we have a sequence of hidden states and their observations, and we see how actually you can get their probabilities. So if you don't know about this, you should follow part 1 of the video series first, and then come back right here. And the link is given in the description. So this is the building block, also for hidden Markov models and the Viterbi algorithm. So what is the decoding problem? I mean, this is what we are trying to solve here. So what's the problem itself? The problem is, what are the most likely sequence of hidden states when you are given an observed sequence of events and the HMM model? Let me elaborate this. Suppose these are your observations. So V3 means you have a high ctDNA level. So high ctDNA, moderate ctDNA, then low, and low ctDNA. So you have these 6 observations. Now you're asking, what are the cancer stages in these 6 time steps? So what are the Qs? What are the hidden states? So that is what we are going to have to actually solve in the decoding problem. And I want to tell you one thing, that this decoding problem is actually the most widely used problem of HMM. So one simple way is we actually look at different possible combination of hidden state sequence. For example, maybe we say that, okay, if the 6 hidden states at the 6 time points were Q3, Q2, Q1, and obviously observations are given, then what is the P1? What is the probability of that? We can ask the same question for a different combination of Qs, and we can actually do this for all the different combinations. Since in this example, there are 3 possible states and there are 6 time steps, so there are 3 to the power 6 possible such combinations. And if we take the combination or the sequence of hidden states with maximum probability value, then that is going to be our answer. So suppose if the last one, which is the PM, actually has the highest probability, which is basically PM, then that is going to be our answer. So we are going to say that it started with early stage, then mid stage, early stage, late stage, and then late stage. That's the answer. But this is not feasible because, as you can see, if we have only 10 possible states and the sequence length is 50, then the state space is already very huge, right? So it's an exponentially growing space. So we cannot do this. We need to find some algorithm which is polynomial in runtime. And that is where Viterbi algorithm comes into place. So now let's start the Viterbi algorithm. Let's start with an example. So suppose we have these 3 types of observations available, low, moderate, and high ctDNA level. And we have these 3 hidden states, these 3 possible hidden states, early, mid, and late. And we are going to denote them by small letters and capital letters respectively. So these are the things that we observed in the 3 time steps. So in time step 1, we have high tumor level. In time step 2, we have the medium or moderate tumor level. And in the last time step, we have again the moderate ctDNA level. So what is the Q1, Q2, and Q3 here? So these are Qs. These are the Qs. So what will be the Q1, Q2, and Q3? That is what we have to find out. So this is how we can represent this problem as. So in the first time step T1, we have observed H, a high ctDNA level. Then in T2 we have M, in T3 we have M. We can have any combination of these 3. So suppose this combination that we are seeing in the green arrow is actually the best combination. Suppose. So that means the answer will be late stage L, then moderate, then medium stage M, then again mid stage M. That will be the answer of Q1, Q2, and Q3. And this sequence will have the highest likelihood or probability value. Now again, this is the answer, but how do we get to this answer? That is what I'm going to describe now. So we have to go step by step. So we have to start from T1 and we have to calculate a quantity called delta 1. So delta 1 is for time step T1. So delta 1E, delta 1M, delta 1L. And it is quite intuitive how this is calculated. So this is the power probability, PE, and then probability of H given E, the observation probability. And we can do the same thing for the other ones as well. So this is the base case basically. This is the base case for time step 1. So time step 1 is very easy. But what about the other time steps? For example, time step T2, right? What is the second time step? What are we doing there? So you can see that we can reach this state. Let's just focus on this one state, which is again the early stage cancer. So we can actually come here from E, M, or L from the previous time step. And we can get the probability value for getting from each state to the early stage as P1, P2, and P3. So P1 is equal to, as we know, del 1E, we already stored this, del 1E into the transition probability into the observation probability of M, given that we are in a state E, right? So we can actually calculate this for P2 and P3, the other two arrows. And suppose the maximum probability that we have is P3. So P3 gives us the maximum probability. That means that this is the only arrow we should keep. So if we actually say that in the final time step, we are in the earliest stage of cancer, which is a particular state, then what we can say is in the earlier time step, actually we were in the late stage cancer. Given that we have this high and moderate ctDNA level in the two time steps, that is what it means basically. Okay, and we can actually do this for the other ones as well. For example, we can do the same calculations for the second state of T2, which is the moderate, medium, or mid cancer stage. So we can calculate P1, P2, P3, and suppose P3 is the maximum. So we keep this arrow. We say that if at the second time step we decide that the patient had a mid-stage cancer there and obviously a moderate level of ctDNA, then in T1 it should have a late stage cancer given that we had a high ctDNA level, right? So in conclusion, we can calculate all those things and we can get these arrows. So we know where each of the T2 states actually should come from in T1. I think you can now guess what we're doing again. If you watched part 2 of this video series where I discussed forward backward algorithm, you know what to do. So we are going to now calculate T3. So in T3, we are going to transition from T2 and we are going to again in the same fashion calculate P1, P2, and P3, but this time we are going to use delta 2 because gradually we are going forward. And suppose P1 is the maximum probability, so we are only going to keep that. So del 3E is going to be P1. Right? Del 3E is going to be P1 because P1 is the maximum. Now this is basically the formula for calculating this del Tj. J is the state J. And this is what we have been doing. We have been getting these probability values and we have been getting the maximum one, right? And assigning that to del. So I didn't want to show you this formula initially because that will confuse you. But now that you can see it, you know what this means. So suppose this is basically our final diagram. So we have all these arrows right here. We know where we should come from. Now, what is the decision? Like, how can we decide what should be our most likely sequential states? So first of all, what we need to do is we need to actually look at these three values, these three delta values at the very last time step, because this is the cumulative probability, right? So everything accumulating to del 3E, del 3M, del 3L. Now, suppose the maximum one is del 3M. So if del 3M has the maximum value, then this is the answer. This is the state. This is the last or most probable state. So this should be M. Then if we backtrack, we know the ancestors. We have kept track of those. Then the previous one should be again M. Then the previous one should be L. So we have L, M, M. Right? That's how easy it is. You just keep calculating these del values. At the final time step, you just get the maximum one and then you backtrack. So that is all you have to do. And this is very efficient because the runtime is big of n squared t because n is the number of hidden states basically. So you can see that we're calculating sort of a lattice, a 2D lattice. That is why it's a nested operation. So it's n squared. And we are doing this for t time steps, right? For T1, T2, T3. So it's n squared t. So it's polynomial, it's very fast and it's good to use. So that's all about Viterbi algorithm for you. So if you like the video, feel free to subscribe and share. And you can donate to our channel via the donation link. So in the next video, we are going to talk about HMM training, which is the Baum-Welch algorithm. And that's, I think, the most critical part of HMM because that's a very tricky algorithm, I would say. I would try to explain the ins and outs of the algorithm in the next video. The link will be given in the description. Thank you.